Hello, beautiful people, and welcome back to Unit 6 of Regions Chemistry, which is about the periodic table. So today we'll talk about some of the trends that we see in the elements in the periodic table. So the first trend that we'll talk about today is the atomic radius, which is the distance between the nucleus of an atom and its valence electrons, or the outermost shell. So this is what the trend looks like for atomic radius specifically. Now, what we mean by a periodic trend is that what happens to whatever thing we're talking about. So like right now, we're talking about atomic radius. So what happens to the atomic radius as we go down the group or as we go like across the period from left to right? So this is what it looks like for atomic radius. And let's look at that in more detail and let's see what this means. Now, if we look at an atom, let's say I am looking at a lithium atom. We have a nucleus in the middle, and then for a lithium atom, we are going to have 3 protons in the nucleus, and we have 4 neutrons. And then we've got 2 orbits. In the first orbit, we have 2 electrons, and then in the second orbit, we have 1 electron. So atomic radius is basically this distance right here between the nucleus and between the electrons in the outermost shell, or the valence electrons. So what happens to this atomic radius as we go down the group? Let's look at some of the elements. Here I am looking at the elements from group 1. We've got lithium, then we have sodium, then we have potassium. So in lithium, once again, we have the nucleus in the middle, we have the protons and the neutrons, we have 2 shells, and we've got 3 electrons. Okay, in the sodium, we have once again got the nucleus. Now notice how this nucleus has more protons, it has more neutrons, and then we have 3 orbits, and here we've got the electrons in them. Okay, and then we have potassium. Once again, here is the nucleus for potassium. Once again, we've got the protons, which are way more than the sodium now. So here are all the protons, then we have these neutrons, and then we have got 1, 2, 3, 4 orbits, and here we have got the electrons in these orbits. Alrighty, so if you guys go to table S and you go to the column that says atomic radius and you look for the atomic radius for lithium, sodium, and potassium, these are the numbers that you get. 155 for lithium, 190 for sodium, this for potassium. Now, notice what's happening to this radius. It is increasing as we are going down the group. The reason why that is happening because as we go down the group, the number of orbits is increasing because lithium is in the second period. There are only 2 orbits. Sodium is in the third period. We now have 3 orbits. Potassium is in the fourth period. We now have 4 orbits. So every time we go down to the next period, as we go down the group, we are increasing an orbit. Now, when the orbit increases, the radius also increases because now we have a longer distance between the nucleus and the outermost orbit. So that's how, as we go down the group, atomic radius increases. Now let's see what happens to the atomic radius as we go across the period. So now we are looking at period 2. So we have lithium in the very beginning of that period, and then we have fluorine pretty much like towards the end of the period. So this is what lithium looks like. We just looked at that. And then we have the fluorine. So we have the nucleus in the middle, we've got the protons and the neutrons, and as you guys can notice, the number of protons and neutrons in fluorine are is greater compared to lithium. So fluorine has more neutrons, it has more protons. And then we have the same number of orbits, we've still got 2 orbits, but in this case, the first orbit still has 2 electrons. The second one, however, has 7 electrons. Okay, so that is something that's changing. Now, if you guys go to table S and look at the atomic radius for lithium and fluorine, these are the numbers that you get. So notice how as we are going across the period from lithium to fluorine, the atomic radius is decreasing. And the reason for that is because the number of protons is increasing as we go from the beginning of the period all the way to the end of the period. Now, because of that increased number of protons, there is a stronger nucleus pull on the electrons. So the nucleus is pulling the electrons very, very strongly now, and that actually decreases the atomic radius, which is why as we go across the period, the atomic radius decreases. So now you guys know how we got that trend that we saw in the beginning. And this is how we represent that trend in chemistry terms, like on the periodic table. For the most part, you guys will not ever be asked to draw the arrows, but this is just a nice way to kind of remember what's happening in this specific trend. So basically what we do is we draw the arrows towards the position in which that specific thing is increasing. So what these arrows are telling us is that that long arrow across the period is just saying that the atomic radius is the largest, it's the greatest at the beginning of the period, and it's the smallest like towards the end. And then that down arrow is representing that as we go from the top to the bottom, the atomic radius increases, which means at the top, atomic radius is smaller, and then at the bottom, atomic radius is larger. Okay, next up we'll talk about the trend for the ionic radius, which is once again because it's a radius, so it's going to be the distance from the nucleus to the valence electrons. But in this case, rather than looking at the atom, we are looking at the ion. So remember, ions either have more or less electrons. So some things to remember or recall actually from what you have learned previously. Ions are charged particles, and remember that metals lose electrons, so they make cations or positively charged ions, and non-metals gain electrons, so they make negatively charged ions, which are called the anions. So the rule here is that when we talk about the cations or the positive ions, because they are losing an electron or two, or more than two, because they're losing electrons, their ionic radius is less than the atomic radius. So for example, if you look at magnesium here, magnesium has two valence electrons. When it becomes an ion, it loses those two electrons that are in the outermost shell. Now, when it loses both of those electrons, there's nothing left in that shell, so that shell is also gone. So now the magnesium ion with the positive 2 charge has the second orbit as its valence shell with 8 electrons. So now you guys notice because it has less orbits, it is also going to have a smaller radius compared to the actual magnesium atom. So the easier way to remember that is because cations lose electrons, their ionic radius is going to be less. So L for lose, L for less. Alrighty. And then the rule for the anions or the negative ions would be that because they are gaining electrons, their ionic radius is going to be greater than the atomic radius. So for example, when we are looking at this chlorine atom right here, it has 7 valence electrons before it gains another electron and has a complete octet. So all it's doing, its nucleus is still the same, but it is adding more electrons in there. So the nucleus pull is still going to be the same, but because we have more electrons, the atomic radius is going to be greater than what it was before. So easier way to remember that is gain electrons, so G for gain, and G is for greater ionic radius. Alrighty, so the next trend that we'll be talking about is the ionization energy. So ionization energy is the energy that is needed for any atom to lose one or two of its electrons. Now, if the ionization energy is low, then that means there's very less amount of energy required to lose an electron. So that which means it is easier for that atom to lose its electrons. Now, the thing to remember here is that metals want to lose electrons. Now, because they already want to lose electrons and it's easier for them to lose electrons, that means they are going to have low ionization energies. Non-metals, on the other hand, want to gain more electrons. So because it's not very easy for them to lose the electrons that they already have, they are going to have very, very, very high ionization energies. So let's look at what the trend for ionization energy looks like as we go down the group and across the period. So let's talk about down the group first, starting with lithium. This is what the lithium atom looks like. And if you keep going down in the same group, and let's pick potassium, this is what the potassium atom looks like. And then you guys look at table S for the ionization energy for both lithium and potassium. And these are the numbers that you get, right? So if you guys can notice how the ionization energy is decreasing as we go down the group, which means the elements that are at the bottom of the group require less energy to lose their electrons. So it's very easy for them to lose electrons. And the reason for that is because as we go down the group, the number of orbits are increasing. And because the number of orbits are increasing, the electrons are going away and away from the nucleus. So there's less pull and less attraction from the nucleus. And because of that, there's nothing holding those electrons back. So it's very easy for those electrons to just go. And we don't really need a lot of energy to break free those electrons from the pull or attraction from the nucleus. Now let's look at what this trend looks like as we go across the period. So once again, we are now comparing lithium and fluorine. So lithium is on one end of the period and fluorine is all the way at the other end. Remember, lithium is a metal and fluorine is a non-metal. Both of them are very, very strong. Lithium is a strong metal, fluorine is a strong non-metal. So that means lithium would want to do anything out there to just get rid of its electrons, and fluorine would never ever want to lose any of its electrons. It's very hard for fluorine to even imagine that I'm going to have to lose my electrons. And here's the reason why. When we look at lithium, this is what lithium looks like. It only has one valence electron. When we look at fluorine, it has 7 valence electrons. It only needs that one more electron to have a complete octet. Okay, and if you look at table S to compare the ionization energies for both, this is what the ionization energy for lithium looks like, and this is what it looks like for fluorine. A lot of energy required to for fluorine to lose an electron. And the simple reason for that is because as we go across the period, the number of valence electrons are increasing. So now those elements would want to gain electrons rather than losing them so that they can have a complete octet. So this is what that trend would look like on the periodic table. So we'll say that as we go across the period, the ionization energy is increasing, so we need more and more and more energy those elements need more energy to lose their electrons. And as we go up like down the group, the ionization energy decreases. So basically the ionization energy is the highest or the most at the top of the group compared to at the bottom of the group. Okay, so that is the place where those elements, like on that side of the periodic table, have the highest ionization energies. And remember, those are also the nonmetals. So now it kind of proves what we said before, that nonmetals tend to gain electrons rather than losing. So they have very high ionization energies. It's very hard for them to imagine losing their electrons. Okay, now the next trend that we will be talking about is electronegativity. And electronegativity is the ability of any atom to attract the electrons of other atoms out there. So basically just think about it as a recruiter. So we are talking about these elements which are recruiting the electrons of other elements. Just like we have this one college which is just recruiting the students from other colleges by showing them the great programs that they have. Okay, so remember that if we are looking at an element that has a very large electronegativity, then that means that atom is definitely going to attract more electrons and it is going to gain more electrons in return as well. So just one thing to remember is that metals want to lose their electrons. So if they want to lose them, there's no way they would really want to attract more electrons because they want to get rid of theirs as well. Why would they get more? But nonmetals, on the other hand, do want to gain. So they will be the one out there who will be recruiting and looking for other elements. So as you guys can guess from this information only, that nonmetals are going to have higher electronegativities compared to metals. Let's talk about their trends. So once again, let's compare lithium and potassium. This is what lithium looks like. This is what potassium looks like. Very, very large compared to lithium. And if you guys go to table S and look for the electronegativities for lithium and potassium, these are the numbers that you get. So why is that? Why is the electronegativity decreasing as we go down the group? Well, because the number of orbits are increasing. That's once again the first reason for anything. The number of orbits are increasing as we go down the group, and because of that, the outermost shell is now going away and away from the nucleus. So those outermost shells are themselves not having a lot of attraction from the nucleus. Then how come will they have attraction to like attract an electron from any other atom? Okay, so it's kind of like these are some people living in the same room and they're not even friends with themselves, but then they're like, how are they going to be friends with people that are not living in their room? So that kind of thing. So because of that lack of attraction, the electronegativity is going to decrease as we go down the group. Now, if we talk about that across the period, once again, we are comparing lithium and fluorine. Lithium, a very strong metal, fluorine, a very strong non-metal. This is what both of them looks like. Lithium is on one side of the period, and then fluorine is all the way at the other end of the period. So the only difference between both of them have two orbits in their atom. The only difference is that they have, like lithium has less electrons, protons, and neutrons. Same thing with fluorine. So lithium has only one valence electron and fluorine has seven. So lithium doesn't really have that motivation to gain more electrons because it's only got one. It's like lithium is like, how much work do I have to do to get seven more to become stable? But fluorine is like very motivated because fluorine is like, I'm almost there. I'm very close to the finish line. I've only got one more to go. So when you compare their electronegativities by looking at the periodic table, clearly fluorine has a very high tendency and motivation to attract more electrons. So basically, that's the only reason why electronegativity increases as we go across the period, because the number of valence electrons are increasing. So those elements are much more likely to attract more electrons and then gain those electrons compared to the elements that don't have a lot of valence electrons. So the trend for electronegativity is very similar, actually exactly the same as ionization energy. So non-metals are going to be the ones that will be attracting the most electrons. So basically, as we go across the period, electronegativity is going to increase. And then as we go down the group, electronegativity is going to decrease. So basically, this is the part where we'll have the most electronegativity, and that is the part where we have all of the nonmetals. Alrighty guys, so here we have finished unit 6, the chapter on periodic table of elements. So congratulations, and I'm gonna peace out with that. I'll see you in the next one.